Hey guys, so in this tutorial we'll be talking about kind of the idea for this tutorial is duality, okay? And we're going to basically discuss a bunch of really important ideas in machine learning, and actually, in my opinion, some of the most beautiful um, kind of approaches to machine learning, which are kind of mathematical. They're really elegant, so it's a little bit more mathematical today, but hopefully you'll see how kind of powerful this idea of duality and kernels that we'll be talking about today are. So, okay, so what is duality? I just want you to think about duality as um, a different uh, a different perspective. Um, so, what do we do in machine learning, or so far in machine learning? We kind of we look at the primal form. Okay, so let me put these on two sides here. So we have primal versus dual, and basically primal is what we've been doing all along, which is we consider learning a weight vector w equals to, or w being some vector in our P, where P is the space of dimensions, right? So for linear regression, we have w0 plus w1 xi 1 plus 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 wp xip, and then the goal is to learn w0, and in that case, w hat is x transpose x inverse x transpose y. But not only in in linear regression. This is the same kind of approach we do in logistic regression. This is the same kind of approach we do for linear classifiers and for perceptron learning. Last week we saw also that we learn W, right? Because you learn, you look at the two clauses that are linearly separable, hopefully, and you have a hyperplane, and then this vector here is the W vector, and the goal of perceptron learning is to learn W. Okay, the dual is a different approach. Okay, and basically in this case, I like to think of the dual as kind of an approach where we focus. So here we're looking at weight space, right? But here we're going to focus on the data points. Okay, and what I mean by that is that here in the weight space view, we have P parameters, right? Here we're going to have, usually we'll call them alpha 1 to alpha n. So we're going to have a parameter for each data point. Okay, so hopefully you see the difference. If my data set is composed of xi, yi pairs or xi, ci pairs, and we have a total of n, capital N data points. Okay, in the primal, in the weight space view, we pick some p, right? You pick a p-dimensional space where your features are going to lie, and then you kind of build this model looking at the weight space. In the dual view, which is more kind of data centric, I guess. Maybe that's not the right way of putting it, but I mean observation centric. So for each xi, we have n of them. We're going to actually have a corresponding parameter as well. Okay, so you see here that we're going to have a capital N dimensional vector to learn, whereas here we have a p dimensional vector to learn. And the idea behind dual algorithms is that you can actually focus, you can kind of think of alpha I as the importance of xi. So hopefully you kind of intuitively think of your data set, and let's look at this example here. Let me pick a different color. So let's look at this example here. if we look at, say, this point, okay, and let's call this x tilde, and let's look at this point here. Let's call this x bar. Okay. Now you're going to have an alpha I tilde and an alpha I bar, right? So for each of these two data points, you're going to have also a corresponding alpha I, and that captures the importance of these points. Okay. So this one corresponds to xi tilde, this one corresponds to xi bar. Now the question is, which of these two data points is more important for your model? Well, you can kind of see that, this x bar is like really, really deep inside of the class, right? Whereas x tilde is right on the margin, right on the edge. So in other words, you can think about this. If I classify x tilde I correctly, then xi bar is also going to be classified correctly, right? With let's say with high probability, right? And what I mean is that, if I'm classifying x tilde correctly, that means that the line is putting x tilde to the left. Now, because this x bar is so far left, there's very little chance that my model is actually going to be doing the wrong thing at x bar if I'm doing the right thing at x tilde. The only chance is like I get something really weird like this, right? In this case, that's why I wanted to put with high probability, because I just wanted to show you that there are some cases that you could be also making a mistake in x bar. But the point is that these values on the margin are much more important than the points on the kind of like deep inside of the class. And so the idea behind these dual algorithm, actually before I say that, so based on this kind of reasoning, we should expect that alpha I tilde is bigger than alpha I bar, in the sense that if I have the data set, I would prefer to have x tilde I than x bar I. And x tilde I gives me more information about the final model. And so, points on the margin are more important than points deep inside the class, and they give me a better idea of what my model should be. And so the idea behind dual algorithms is to kind of be able to assign an importance to each observation, and then build your model based on that importance. So this is the idea behind SVM, right? SVM, again, we have our two classes, right? I mean, think about perceptron. In perceptrons, we want to have a straight line that kind of separates those 2 points, right? Now, the problem with perceptron is, there's an infinite number of straight lines. These all work, right? The idea behind SVM is that we want the line that actually maximizes the margin. The margin is this kind of this distance. So this is the margin, and we talked about this actually last week. We called it gamma. So it's this gamma. So we want to actually, so we have gamma on both sides. We want to actually maximize the margin, right? That make the margin as fat as possible. And if you think about that, all you really need to know is this point and this point, right? I could throw away all the other points if I just know these 2 points. So we should expect that the importance alpha I for these 2 points is high, and actually the importance for these inside points will actually be 0, right? Those are actually not going to be useful or relevant to computing the margin. And so we actually call these points the support vectors. Support vectors. Okay, and we'll talk about this a lot more. Okay, so I'm just trying to give you a very high-level overview. But the idea is that these 2 things are just 2 ways of looking at kind of the same algorithm, or we're trying to achieve the same kind of objective. but they go about it in two different ways. Okay, so the primal, look at the weight vector, look at the p-dimensional space. Dual, try to identify the really important data points and have a parameter for every data point. Okay. All right. So the first question of this tutorial is to look at the dual perceptron. So remember the perceptron we did last week. If you don't recall what we did there, please go back and review before watching the rest of this. But hopefully you guys all remember it. And let's try to convert, or let's try to basically look at the perceptron from the dual point of view. Okay. So here's the basic algorithm for perceptron from last week. This here means the number of data points. Okay, so you can call this n as well. This is not like the most rigorous kind of pseudocode, but I'm just basically saying we cycle through the data. Maybe we cycle a number of times, and then we check this quantity here, which is the current weight vector WT dot product with the current xi multiplied by the class yi, and if that value is negative, then we need to do an update. We're making a mistake. Okay. So how do we rewrite this to get rid of the w, right? Because this is primal. We're talking about w. We want to basically just get rid of w altogether. And the way to do that is to notice that, okay, well, let's say we make k mistakes in total, right? So assume that there's k updates of w in total, right? So what is our final wk? Well, our final wk, every time we're just taking the old wk, the old wt, and we're adding this correction eta yi xi, and these are happening every time I make a mistake. Okay, so just for the sake of making things easier, let's take eta equals to 1, and we start off with w0, right? And then when we make our first mistake, we add yi1 xi1. So what I mean here by I1 is the index. So I1 is the kind of the index of first mistake or update. Okay, what I mean to say is that so I1 may not be equal to 1, right? We might not update on the first data point that we look at. We might update on the 5th data point. So here I'm just keeping track of the fact that this is not exactly happening at the ith point, it's happening at the i1st point. And then we do this and we make a second mistake at some other index, i2, and we basically just keep adding up to the last mistake, which is going to be k. Okay, so we have a total of k mistakes. Now, if you recall from last week, what is W0? Well, this is usually just taken to be the 0 vector in the p-dimensional space, right? So this is a vector 0 in the p-dimensional space. So this, we can just kind of ignore it and just look at this part. So what I've got here is that WK is equal to the sum, let's say J equals 1 to K of yi j xi j. Okay. Now let's rewrite this. So let me just make a note here, right? Let's imagine that let's say we have our data set. Actually, let's say we have our data set that looks like this. Okay, and let's just say that this point here is x3, and this point here, that's x10. Okay, for example. Now, if we just think about which points are more important, you think these points are more important, right? And you would think that you'd make more mistakes on these points, right? You would make more mistakes on the points that are closest to the margin because the model basically has to calibrate to be in there. So you could imagine that you will make multiple mistakes on this. So imagine that I5 is equal to let's say 10, which is equal to I20, and they're all equal to 3. In other words, I make a mistake on point x3 at iterations 5, 10, and 20. And let's say that I make, similarly, I6 is equal to I8 is equal to I40, which is equal to I50, and they're all equal to 10, which means I make 4 mistakes on x10, and they happen at these iterations, okay? 6, 8, 40, and 50. So what that means is that 4 times in the summation, this xij is equal to x10, and 3 times in the summation, it's equal to x3. So we can simplify this by writing the sum over all data points, alpha I, yi, xi. So what I'm doing here is saying, well, let me actually define alpha I. This is equal to the number of mistakes made at the point xi, yi. So, for most of the xi's, we're not going to make an update, so alpha I will just be 0, right? But for some of the points, we'll make multiple updates. So, for example, here, alpha 3 is going to be 3, right? Because we make 3 mistakes. And here, alpha 10 is going to be 4, okay? And if we take this point here, x20, for example, you could have alpha 20 equals to 0 if you never make any mistakes on that point. Okay, and basically I'm just rewriting this summation as this summation, and hopefully you can see that they're equivalent. But basically I've shifted the focus from W, right? I'm rewriting W in terms of just the data points. So let's look at the dual perceptron. And by the way, I should note, if eta was not equal to 1, if eta was equal to, say, 0.1, this kind of argument still works. It's just that the alpha I changes it changes the meaning a little bit, because you're going to have to account for the fact that there's an extra factor eta, but it's not very important for our purposes at the moment. So anyway, so let's look at the dual perceptron. You're still going to basically cycle through the data. Okay, and now we want to rewrite this condition, yiw dot xi, but we don't want to write w, we want to write everything in terms of the data, or the dual parameters, alpha. So this condition would be yi times this summation. Let me use j, so we don't confuse it with the I. Alpha j, yj, xj. And this is going to be dot product. So this whole thing is a vector, dot product with the ith data point. And we're going to check if this is less than 0. Okay. And then we're going to update W, what was our old update? WT plus YIXI. Well, adding an extra YIXI is like saying, okay, we made a mistake on the ith data point. So what does that mean in terms of the dual update? Well, it means that we should increase alpha I, right, the ith data point importance, to be equal to the old alpha I plus 1, right? Because this is saying we made another mistake on the ith data point. Okay, now that is basically the dual perceptron. That's it. So instead of looking at W, we're looking at alpha parameters, and the alpha parameters are just capturing the number of mistakes made. And this, you can kind of see this as being the importance of xi, right? Because if I make many mistakes on a particular data point, that means that that point is actually quite important for me to understand the model. Whereas if I make 0 mistakes, alpha I equals 0, then that point cannot be that important, because it must mean that it's quite easy to classify. So importance, number of mistakes, difficulty of learning a point, these are kind of all the same idea, okay, or the same notion. And so this is our dual perceptron here, okay? Now, why do we, or what's kind of different about this is, if you look at the update, so now let me write this here. If we look at this condition, okay, this is equivalent to the dot product of xj and xi, right? Because yj, alpha j, these are just constants. These are just numbers. Xj is an actual vector, so we're basically looking at the sum over all dot products in our data set. So let's look at this gram matrix, which I'm going to define in a minute. Okay. Basically, this is basically saying that we only so to do dual perceptron, okay, compute all dot products between your data points. Okay, that's basically it. You can throw away the data set. All you need to keep is the yj and all dot products between your data points. And so this is where the idea of the gram matrix comes in. The gram matrix is the matrix that looks like this. It's going to be x1 dot x1, x1 dot x2, all the way up to xn dot xn. Okay. x2 dot x1, x2 dot x2, so on and so forth. Sorry, this should be x1 dot xn, x2 dot xn, and we're just going to basically keep going all the way till we get to xn dot xn. So this is the last row. So basically, this is just all dot products between the data points. So this is a matrix in n by n, and that's the gram matrix. So this is just a special name that we call this particular matrix. And the idea is that you could basically just store G, just all dot products in your data set, and use that. So in this case, if we rewrite this condition, it's going to be alpha j, yj, g, ji, right? Gji, I mean the jith element. So if you think of this just as an array, this is the jith element of the gram matrix. So what I'm saying here is that literally all you need is g and y. Okay, and so basically to do dual learning, okay, the first step is to compute the gram matrix. Okay, so as long as you have all dot products between your data points, you can put them in a matrix, and you can do dual learning. Okay, and this is not just true for dual perceptron. This is also true for SVM. This is also true for a bunch of other machine learning models. The most famous of which is the Gaussian process. Okay, so basically this is an idea that comes up over and over in machine learning, and we'll talk about it a lot more. Okay, so that is question one. I kind of want to take a detour here and talk about features. Okay, so hopefully you're all familiar with this idea of a feature. The idea of a feature is that you can have some vector. Let's say this is your data set, x1, x2, and you want to basically, these are your features, x1, x2 are your features, but you might want to compute some more features. So for example, you might want to look at, let me call it phi x. Let's say you want to look at x1 squared, x2 squared, log of x1, and maybe, let's say, x1 over x2 squared. Okay, so I'm just making this up, but basically you want to transform your data into something that's a little bit different. Okay, so here's a good question. If I have linear regression, okay, we know that linear regression is W0 plus W1 xi1 plus W2 xi2 all the way up to WP xip, right? This is linear regression. So my question is, can you do something like this, right? W0 plus W1 log of xi1 plus W2 of xi2 cubed, for example, and so on and so forth. In other words, can I transform my x's? And this is linear regression, but can I do this? And the answer is yes, right? It doesn't actually matter what you do to the x's, as long as we are talking about a linear model, which means linear in the parameters w. Okay, so as long as you're not doing anything like this, so you cannot do something like W0 plus W1 cubed log xi1 plus W2, so on and so forth. In this case, you can't. This is not linear anymore. Okay, but as long as you're only transforming the data, then if you're not changing the parameters, this is still going to be a linear model. Okay, so the idea of a feature, or the idea of transforming your data, should be very intuitive. And the idea is that, the basic idea is that your data, could have more information in it, or could be more suitable for modeling if you transformed it. So, a really common example that comes up is in finance, where you might look, or accounting, for example. It's not interesting to know just x1 and x2. You might need to know the ratio between them, right? So I'm not an accountant, but like, for example, book to value ratio is more useful for your model than just looking at either of those numbers in isolation. So in that case, we would look at the feature that is the ratio of x1 and x2. Okay. All right, so hopefully the idea is kind of intuitive. I want to show you how you can use feature transformations to improve on the perceptron and improve on linear models in general, right? Because one of my favorite examples is just to look at this really simple setup. Let's say you have data, and you have two classes. Okay, so data in R, so just one-dimensional data. Okay, and let's say I have two classes, and let's say this is my x-axis, my 0 is, say, here, and the first class looks something like this, and the second class, the negative class, maybe looks something like this. Okay. Now, this is just a one-dimensional data set. I've just drawn the 0. Maybe that's kind of confusing, but just to show you where the 0 is, let me erase this, just to make it really clear that this is just a one-dimensional data set. So the question is, does linear classification work here? So what would a linear classifier be able to do here? Well, if you look at a linear classifier, right, it's just going to be a straight line. So the best you can do is basically classify everything to the left of this as green, everything to the right as red. Or it could do this, okay? Or it could do this. Okay, but it basically cannot be both of these at the same time, right? This is not going to be a linear classifier. So a linear classifier doesn't really work here, right? So no, it doesn't work on the original data, okay? But how do we solve this? Okay, so what are the solutions? Well, there's two solutions. Well, there's probably more than two solutions, but two solutions that I'm going to talk about. The first one is use a nonlinear classifier. So if you remember from last week, I talked about the multi-layer perceptron. Right? The multi-layer perceptron can learn a nonlinear decision boundary, and it could learn something like, say, for example, something that looks kind of, like this. And basically, it could say anything on the upper side of this weird curve is going to be a circle, everything below is a plus. Okay, so this is the orange line. This is kind of a lot of work, right? It's quite complex because you need to come up with a new algorithm, right? You need to come up with a new way of training it. It's quite complex. There might be an easier way. The easier way is to maybe transform the data. So the question is, can we transform the data in a way such that and use a linear classifier? So the idea is that don't come up with a new model. Stick with the same model. Just transform your data. Okay. And in this case, there's actually a very simple transformation, and I'm going to call it phi. So when I write phi, this is kind of a function. It's going to take as input my original vector, and it's going to spit out my transformed x. Okay. So usually with these transformations, you want to go from some, let me write like this. You want to go from some p-dimensional space to some, let's say, k-dimensional space where k is bigger than p. This is not always the case. Sometimes you want to go from p to something smaller, but in a lot of these examples where you need where there's a nonlinear boundary that works, you actually need to project your data to a higher dimensional space. The idea is to go from a one-dimensional space to a two-dimensional space or a five-dimensional space, and then use the linear classifier on the more high-dimensional space. So, for example, consider this function, right? That we take x and it maps to a two-dimensional vector x squared. Okay, so instead of just looking at the value of x, we're going to look at the value of x in the first coordinate, and in the second coordinate, the value of x squared. Okay, so what is that going to do to our example up there? Well, let's actually put some numbers here. Let's say this is -1, this is 1, and let's say this is just to make my life easier, this is going to be 2, this is going to be 3, this is going to be -2, -3, and these points are, let's say 0.5, 0.25, sorry, negative, and these points are 0.25, 0.5, and let's just focus on those four points, okay? So what happens to the point 0.25? Which is just 1/4. Well, if we map it to the new vector, it's going to be the vector 1/4 and 1/16. Okay, so if we look at 0, so now we're going to have a two-dimensional space. We're going to have x1, well, we're going to have x and x squared. So this is the x squared axis, because now we have a two-dimensional vector. The first coordinate is 1 over 4, so it's going to be here. And it's going to be mapped to 1 over 16, so somewhere here. Okay. Similarly, negative 1 over 4 is going to be mapped to this point here. Okay. What about 1 over 2? Well, that's going to be mapped to 1 over 4. Right? Let me just do it up here. What's phi of 1 over 2? Well, this is going to be equal to the vector 1 over 2, 1 over 4, right? 1 over 2 squared is 1 over 4. And similarly, we're going to get negative 1 over 2 being mapped to 1 over 4. Now, what's going to happen to the green points? Well, what's going to happen to, let's say, 2? Well, that's going to be mapped to 2, 4. And what's going to happen to 3? Well, that's going to be mapped to 3, 9. So let's draw those here. So this is 2, this is 3. They're going to be mapped all the way up here, right? And same thing with negative 2, negative 3. They're going to be mapped to these values up here, right? This is what the x squared function does. It's a parabola. It looks like this, right? But what do you notice about the red points and the blue points? I know it's a bit messy, but hopefully you should see that this actually creates or gives us some distance between the red and blue points, and actually a straight line can just classify. So this is a linear classifier. It actually does work in this case, right? I can just basically separate the points with this linear classifier. Okay, so the idea behind transformations is that they can capture information that's not present in your original data because you want to interact with features. But the other way of thinking about it is that maybe in the original feature space in p dimensions, the data is not linearly separable. However, we can project it to a higher dimensional space where the data can be linearly separable. Okay, and again, I just want to stress this is not always true. Sometimes you want to project, sometimes you have very high dimensional data and you actually want to project down to a smaller dimensional space, but that's a different problem. Here I'm talking about linearity and being able to use, or being able to make your data linearly separable. Okay, hopefully this example, this is an example I like to keep in my head when I'm thinking about this and trying to explain this concept. There's actually another more concrete example that I want to show you as well, which is the example of the XOR function. Okay, so XOR function, and again, this is probably the fifth time I talk about this function. So hopefully you remember. Hopefully you remember how it's defined, but if not, I'll just write it up here. So we can have 4 values. Again, I'm using 1 for true, -1 for false, and we have our class y. So when they're both true, this is false. When they're both false, this is false. Otherwise, it's true. And you can actually draw this function x1, x2 axis. So here we have our 1, -1, 1, -1, and so you will actually see that this is going to be negative, negative, whereas these 2 points here are going to be positive, positive. Okay, and when I say positive, I just mean 1, negative, -1. Okay, so this is what our XOR function looks like, and you can very clearly see that it's not linearly separable. Okay, not linearly separable. Okay. So again, we have 2 options. We can use a nonlinear classifier. We actually did use a nonlinear classifier last week. We used a multi-layer perceptron, and we showed the weights that would work for this problem, but I want to go for the maybe slightly easier approach. I want to use a perceptron or a linear classifier, and I want to transform the data. Okay, so let me give you a transformation, and this might look a little strange at first, but we'll talk through it and we'll explain why. So first of all, the original data is two-dimensional, right? We have a vector in 2 dimensions. So we want a feature vector or a feature function that's going to go from R2. In this case, we're going to go to R6. Okay, and I'm going to define this guy as taking my points x1, x2 into this vector. Okay, so this vector is going to be vector 1. The first coordinate of the vector is 1. The second is root 2 x1, root 2 x2, x1 squared, x2 squared, and root 2 x1, x2. Okay, so this looks a bit strange, but it will make a lot more sense in a bit. But I mean, it's just a feature transformation. It could be anything, right? So I've just happened to choose this one. So let's see what this does to the first point. Okay, so let's actually evaluate the feature transformation for the first point, 1, 1. Well, this is going to be 1, root 2, root 2, 1, 1, and then root 2. Right? So hopefully you should see that, root 2 x1 is just 1, so root 2 times 1 is root 2. Same thing here. X1 squared is just 1 squared. X2 squared is just 1 squared. And root 2 x1, x2 is just root 2. Okay? How about phi of negative 1, 1? Okay, well, it's going to be 1. Now it's going to be negative root 2, root 2. This is still going to be 1, 1. And this is going to be negative root 2. Okay? And let's just do all of them. So 1, negative 1. Okay, this is now going to be 1, root 2, minus root 2, 1, 1, and then minus root 2. And finally, phi of negative 1 is going to be 1, minus root 2, 1, 1, root 2. So now x1, x2, they're both negative 1, so the negative cancels out, and I'll get this root 2. Okay, so let's try to plot this function. Now this is going to be difficult to plot because it's 6 dimensions, so obviously that's not going to work. But one thing I can do is just pick a subset of 2 points in the 6 coordinates. So I want to draw a 2 by 2 plot. You can just visualize it. Maybe you can visualize it by looking at a. So let's say, so this is x1, x2 space. Now I want to look at, say, let's see. Let's look at root 2 x1, x2, and root 2 x1. So what I mean is I'm looking at this coordinate and this coordinate, the 2nd and the 6th coordinates for each of these. Okay, and I want to plot what each of these points that I plotted here in the original space. I want to plot them in the new space. Okay. Okay, so let's see. For negative 1 and 1, this one here, right? This is going to be a negative point, and this is also going to be a negative point. And for these two, they're going to be positive points. Okay, just to refresh you. Okay, so let's draw 1, 1, 1. Okay, well, root 2x, so we're looking at this coordinate and this coordinate. Let me do that for all of them. okay, the second, and the fifth coordinate. Okay, so for the transformation of 1, 1, we're going to get root 2, root 2. Okay, so we're going to get a point here. Okay, this is the point that's negative, and the coordinate is root 2, root 2. Similarly, for negative 1, 1, negative 1, negative 1, that's also a negative point. We're going to get the point negative root 2, root 2, right? So this point here. Negative root 2, root 2. Okay, sorry, I actually made a slight mistake. What I'm actually doing is plotting. I just reversed the axes, so I'm looking at root 2 x1 on the x-axis and root 2 x1 x2 on the y-axis rather. Okay, so nothing changes. So this is still correct here. Okay, and then now looking at the positive points. Well, negative 1, 1 is going to be negative root 2, right? So let me use the green. So this is negative root 2, and the last point, 1, negative 1, that's going to be root 2, negative root 2. Okay, so that's going to be here. Root 2 minus root 2. And so it's pretty obvious now that you could use a linear classifier to basically separate these points perfectly. Okay, so the transform data is linearly separable. Okay. So in other words, we would basically get so the idea would be 1. So let me learning XOR with a perceptron. Okay, the first step would be transform data. So you would go from x to phi of x, and let's say this is in p dimension and this is in k dimension. Then 2, you would do perceptron training on the transform data. Okay, and now this is not really talking about primal or dual. You can do either one. Here I'm going to basically just, I guess, focus on primal. So the W vector is going to be a k-dimensional vector, right? You need to learn a k-dimensional vector rather than a p-dimensional vector. So for this example, our W would be a 6-dimensional vector. And basically you can see that, so W would be this vector, W0, actually would be a 7-dimensional vector, W2, W3, W4, 5, 6, and 7. Sorry about again, this is the bias, and then we would have, oh, actually, sorry. So it would be a 7-dimensional vector. It would be the bias term, and then 6 components for each of these guys, okay? And you would basically just do the standard perceptron training with this new vector. Now you know that this is going to work because I can basically take I can take every single one of these to be 0 except for W1, except for W2 and W5, right? Because we know that in this 2-dimensional space, we will definitely get a linear classifier that works, okay? So all we need is really W0, W2, and W5. So you might ask, okay, what was the point of doing this what was the point of going to this 6-dimensional space? We could have just gone to the space where we use this transformation phi tilde, which goes from x1, x2 to root 2 x1, root 2 x1, x2, right? There was really no need to go to a 6-dimensional space. You could have gone to just a 2-dimensional feature transformation, and you would have stayed in the same dimension. That actually works as well. Okay. The reason I use this particular feature vector will become a bit clearer. Will become clearer in a little bit. Okay, but let me just go back to the perceptron. Well, let's say that we were doing the dual perceptron. With transformed data. Okay, we know that in the primal perceptron you just use a weight vector, that's a higher dimension, k dimensions, but you just do the same algorithm, right? What about for the dual perceptron? Well, for the dual perceptron, remember we had this condition: if yi j equals 1 to n alpha j yj xj dot xi. Okay, the only thing that's going to change is that now your data points are not xj xi, they're going to be phi xj phi xi, right? You're going to be transforming them to the feature vector. So this is going to be phi of xj phi of xi. Okay, that's really all that changes. And then you need your gram matrix. Your gram matrix is going to be the dot product between all your data points, but your data points then are transformed. So now you're going to have phi x1 dot phi x1, and you're going to keep going and compute all dot products between all n data points. So again, you're still going to have an n by n matrix, but now it's going to be the dot product between the feature vectors, the feature transformations. Okay, so what would be the problem here? Okay, well, the problem is that you need to basically compute this n by n vector. You need to compute all pairwise dot products between all your data points, and now to add to the complexity, you're actually transforming your data to a higher dimensional space, which is even more problematic. Dot products between high dimensional vectors can be expensive, right? Computationally expensive. So think about it. If my transformation was going from R2 to R10,000, for example, you could do that, right? You could think of a lot of useful transformations take you from a very low dimensional space to a very, very high dimensional space, because in high dimensions, right, the idea is that in high dimensions, things are so spread out that it's going to be really easy to find a linear classifier that just is able to separate the points. Okay, the idea is that high dimensionality is actually your friend in these scenarios. So it's kind of the reverse of the cursive dimensionality. In the cursive dimensionality, it's really hard to compute distances between things because things are so spread out. In this case, the fact that things are spread out is actually really useful because you want to basically stick a linear surface, a linear hyperplane in between the two classes, and so projecting them to a very high dimensional space can actually be useful. So so this idea is really nice. The problem is that when you have these really high dimensional vectors, you need to compute dot products between very high dimensional vectors, and you need to do it n squared times, right? Right? You need to compute all pairwise dot products, and so this can be extremely expensive. So let's look at the example, and now it should become clear why I use this particular choice of feature vector. Okay, let's compute the dot product. Okay, let's say x and x prime are vectors in 2 dimensions. So x is going to be equal to x1, x2, x. Well, actually, let me just use y to make things really clear. So x and y. So this is going to be my y vector. Okay, and let's say I take the dot product between the feature transformation of x and y under this feature transformation here, this 6-dimensional feature transformation. Okay, so remember I have to do this for all cases, this is just a 6-dimensional dot product. It could be much larger, but I just want to illustrate the idea here. So this is going to be the dot product of 1 root 2 x1 root 2 x2 x1 squared x2 squared and then root 2 x1 x2 dotted with the vector which is the feature transformation of y, so 1 root 2 y1 root 2 y2 y1 squared y2 squared and then root 2 y1 y2. Okay, so how do we compute dot products? Well, we just take the summation, we multiply the coordinates and we add them all up. So this is going to be 1 times 1 plus root 2 times root 2 is going to be 2 x1 y1 plus 2 x2 y2 plus x1 squared y1 squared plus x2 squared y2 squared plus 2 x1 x2 y1 y2. Okay, so basically every time you want to compute an element of this matrix here, you need to basically add up these 6 terms here, okay, which is kind of problematic because you want to do this n squared many times. So if you have a large data set and if you use a feature transformation that takes you to a much higher dimensional space, say 100, 200, this is going to scale poorly, okay? So why did I pick this particular 6-dimensional vector is because of the kernel trick. Okay, and this is kind of the foundation for a huge amount of machine learning, and it's the reason why we can use these really seemingly kind of computationally expensive models with ease. Okay, so if you look at this guy here, you can actually rewrite it as the dot product x dot y squared. Okay, so I won't prove this, but you can, well actually, let's just prove it. So 1 plus x dot y squared, this is going to be 1 plus, so this is x and y in the original space, so x1, x2, y1, y2 squared, so this is going to be 1 plus x1, y1 plus x2, y2 squared, and now if I expand it all out, I'll get you will get, well, I don't want to rewrite it, but basically you will get exactly this expression down here, okay? Now, the reason this is called the kernel trick is because I'm actually computing the dot product between these high-dimensional vectors, 6-dimensional vectors, by looking at a function of a dot product of 2-dimensional vectors, adding 1 and then squaring. So this is much cheaper to compute than actually computing the entire dot product. Okay, and the kernel trick basically is computing the, and we'll call this, say, kxy. The kernel trick is being able to compute the dot product by just evaluating a function kxy. So you want to compute the dot product between these high-dimensional vectors, but you don't want to do the work of actually writing this out, computing the actual feature vectors, then taking a dot product in this high-dimensional space. You can actually compute the value of a kernel, and the kernel is usually a function of the dot product in the lower dimensional space. Okay, that's the kernel trick. And then what happens is basically that instead of computing these dot products, you would compute the evaluation of the kernel at the 2 points. Well, at all combinations, sorry, x1, 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 x2, x1, xn, so forth. So now instead of computing this high dimensional dot product, you just compute this simple function of the lower dimensional dot product. And so this is the kernel trick. This is a particular kernel called the polynomial kernel. Okay, and the polynomial kernel in general has a form that looks like this: m plus x dot y to the power of d, where m is just some real number and d is some integer. So this sign means natural number, so it's just the set 1, 2, 3, so on and so forth. So if I look at this particular choice, so m is not really that important because it's constant. What's really important is this value of d. In this case, I took d to be 2, right? So when I take d to be 2, this is kind of equivalent to representing my vectors x and y in this higher dimensional space where the actual values of the constants aren't important. What's important is that I'm looking at the linear terms, x1, x2, y1, y2. I'm looking at the squared terms, x1 squared, y1 squared, x2 squared, y2 squared. And I'm also looking at the interaction between x1, x2, and y1, y2. So you know in linear regression, you might have terms where you're looking at the interaction between two features. So basically what this means is that just by computing this value, kxy, I'm getting all of that for free. I'm getting this representation of this two-dimensional object in 6 dimensions with those particular features for free without actually having to compute them explicitly. Okay, and that is basically the idea behind the kernel trick. Now, if I took, so what I wanted to write here was that when I take d to be 2, I get quadratic features, linear features, and I also get first order interactions. Right, first order because I'm looking at interactions x1, x2. So if this was say a 3-dimensional, if I had x3, y3 here, right? First order means I would get x1, x2, x1, x3, x2, x3, right, in my vector. So just by computing this kernel, I get these features. What if I look at another polynomial kernel? Let's say to the power of 10. Well, then I'm going to get features x to the power of 10, y to the power, so x1, y1 to the power of 10. I'm going to get, all the features below that, x to the power of 9, x to the power of 8. So I'm going to get these polynomial features. Okay, that's why this is called the polynomial kernel. But I'm also going to get all the interactions, all the up to 9-way interactions between the elements of x, elements of y. Okay. So that's kind of the beauty of this kernel trick, is that I can get these really, really high-dimensional representations, really detailed representations, without ever having to actually compute any of these features by hand. And the reason is we only need to compute dot products between the feature vectors. We don't actually need the vectors themselves. And to compute dot products, you can just compute kernel valuations. And the larger that you take D, the more and more features you get. Okay, so dual learning. Let me just summarize this. Only need dot products between data vectors, not not the actual data vectors themselves. So we avoid direct or say explicit computation of phi x and just choose a kernel and we just basically compute kxy, and that gives us this phi x dot phi y for free. Okay, so the point is that we never actually have to bother computing features at all. We just have to pick a kernel, evaluate the kernel over the n data points, come up with a gram matrix, and just move ahead with the actual training. Okay, and this is the kernel trick. The kernel trick is avoiding. This is the idea is that you want to avoid any kind of explicit or computationally heavy work. Okay, and this idea is it's pretty huge. It's the reason SVMs are so popular. It's the reason Gaussian processes are so popular, and it's the reason kernel regression is so popular. So without this particular trick, none of that would be possible. So it is useful to know this and understand this. Now, I just want to show you one more example of a kernel. It's probably the most, I guess, famous kernel is the Gaussian kernel. Okay, and the Gaussian kernel actually looks exactly like, or very similar to the Gaussian distribution. I'm going to show you an example for one-dimensional data. So let's just take x1. Let's just take x and y in one dimension, so just real numbers, and let sigma be some positive number. Okay, and okay, let me just refresh you, or let me just kind of recap quickly. When I use this polynomial kernel, right, it gives me a higher dimensional representation. In this case, it was 6 dimensions. When I looked at this to the power of 10, it's going to give me some big number, but it's going to be finite, right? Here, the Gaussian kernel actually gives you an infinite dimensional representation. So that sounds a bit weird, but I'll show you how. Okay, so it actually represents each of the points as an infinite dimensional vector, or feature vector. Okay, and the definition of the Gaussian kernel is the exponential of the negative 1/2 sigma squared x minus y squared. Okay, so this is the definition of the Gaussian kernel, and you should know that this is exactly the Gaussian distribution, right? The Gaussian distribution is 1/√2 pi sigma squared e. Right, this is the Gaussian distribution. This is the Gaussian kernel. So we're just basically removing this and looking at the difference between points rather than the difference between x and its mean. Okay. Now, this is going to be a little bit advanced, so it's not examinable or anything like that. But I just wanted to show it to you because it's quite nice. I'm going to use a Taylor expansion of let me first write this out. So this is going to be the exponential of, so if I just expand the quadratic term, I'll get x squared plus y squared minus 2xy. Okay, then if I break this up a little bit, this will be the exponential of negative x squared over 2 sigma squared, the exponential of negative y squared over 2 sigma squared, and then the exponential of x, y on sigma squared. Okay, and I'm not sure if this has been covered in the previous course, but you can basically just go to Wikipedia and check this out. The Taylor expansion of E of x. So what is a Taylor expansion? It means basically an approximation of a function using a polynomial. Okay, we don't have to worry about it too much, but just note that you can write Ex as the sum from k equals 0 to infinity of x to the power of k over k factorial. So basically, like what I'm doing here, or what this is doing, is taking a function, and you can always take a function and kind of find the approximation of it in terms of a linear, like, this is going to be x to the power of 0 over 0 factorial plus x to the power of 1 over 1 factorial x squared over 2 factorial. So if you look at this, this is going to be, 0 factorial. This is going to be 1 plus x squared over 2. So you see this is a polynomial, and as I keep increasing, I add polynomial terms, and I can approximate the exponential function better and better as I take more and more terms. So the exponential function has an infinite expansion that looks like this. Not so important for us, but it's probably useful to keep this in mind if you do future machine learning courses. Now, what I'm going to do is rewrite this guy in terms of its Taylor expansion. So then I'm going to get the summation from 0 to infinity. I'm going to have xy to the power of k divided by k factorial. But I'm also going to have this sigma squared term, right? So this is going to be sigma 2k, because the sigma squared gets to the power of k, and so I got this sigma 2k. And rewriting it once more, just to kind of separate the terms, I'll get xk to the power of k factorial sigma k. Sorry, this should be root k factorial. And then the second term should be yk root k factorial sigma k. Okay? And basically what I want to show here is that this can actually be rewritten as the dot product between two vectors, phi x and phi y, where they're actually infinite dimensional vectors. And these vectors are going to be, well, let me just write it here. So phi x is going to be the vector that looks like this, minus x squared over 2 sigma squared, times the infinite vector 1 x over sigma root 1 factorial x squared over sigma squared root 2 factorial, and so on and so forth for an infinite number of terms, okay, transpose. So what this means is that using the Gaussian kernel is equivalent to projecting your data points into a feature space. Okay, so x gets projected to phi x and y gets projected to phi y, where this feature space is actually an infinite space, right? This is an infinite 1 x over something, x squared over something else, x cubed, x to the power 4, and so on forever. So you couldn't actually explicitly compute this dot product, right? Well, I mean, you can, but it's kind of weird to think about it, that you're actually getting this dot product between infinite dimensional vectors for free just by evaluating this function. And the really important part is that this function, right, is just a it's just a function of the original vectors, right? These low dimensional vectors. All right, so that is the kernel trick, and this is not really specific to dual and primal perceptrons, but it's just something important that should be noted. So when you're computing this, when you're doing, for dual perceptrons, when you're doing this idea where you project the data into a higher dimensional space, instead of computing all these dot products, you can actually just do if yi j equals 1 to n, alpha j yj, so it should be a j, k xj xi. Okay, so you can just basically replace any kind of dot product with the evaluation of the kernel. The evaluation of the kernel is much cheaper to do. Okay, so far we've basically introduced the idea of dual perceptrons. We've said that in dual perceptrons we just need dot products. Then we went on to compute or introduce the idea of feature vectors. We showed how feature vectors are really useful for classifying seemingly non-linearly separable functions like this one. And then we talked about the added complexity of computing dot products between very high dimensional feature vectors, and then we showed the kernel trick, which lets you do that basically for not for free, but for a much cheaper cost than you would have to with the naive approach. Okay, so the next step for this tutorial is to kind of use these ideas and talk about SVMs. Okay, so SVM is support vector machine. Okay, and machine is just like a really outdated term for algorithm. So this is just the support vector algorithm. And support vectors, you can think of it as important vector. Important and vector is just data point. So, I mean, support vector machine sounds, pretty intimidating, but it's really just jargon for an algorithm that finds the important data points, right? And this goes back to the idea at the beginning of the tutorial where you have two sets of data points, and the ones on the edge closest to the the ones furthest out from the cluster centers are the important points. Those are going to be called the support vectors. All right, so okay, so for SVM we have two objectives. Okay, the first objective is identical to the perceptron. We want to classify all points correctly. Okay, so we're not allowed to make any mistakes. But the second objective, which kind of makes a support vector machine different to the perceptron, is that we want to as large, or usually they'll say fat, a margin as possible. Okay, so we know what a margin is, and we want a fat margin, meaning we want a lot of space between the two classes. So we want the particular hyperplane. So if we draw the picture, let's say this is class positive, class negative. We don't want just any model that separates these two. Okay, this model can separate the two, but it's going to have a very small margin. We want this model here, because this actually kind of, if we think of the margin as being this, okay, we want it to be as fat as possible. So I'll call this gamma. Okay, now the other way to think about it is like you're fitting a rectangle, right? Think of it as a rectangle, and you want the widest possible rectangle that still fits in between the two classes, such that it touches, it intersects with one of the points on either side. Okay, so we just basically keep increasing the size of the rectangle and changing the angle of the rectangle until we get something as fat as possible. All right, so the picture in the lecture notes is a bit clearer, so let me try to draw that. So in the lecture notes, we have our hyperplane as usual, but we'll be talking about the bias or the threshold term on its own now. Okay, so before, we were talking about the W tilde, which includes the bias term. So this would have been W transpose X tilde equals to 0. But now we're going to be talking about the bias term actually on its own for SVMs. And then we have the and the two hyperplanes above and below. Okay, and these are W, maybe I'll just write W dot X equals to T. So this is shifted upwards plus M, and this is shifted downwards by M. Okay, and we have our weight vector W, which is perpendicular to here, and let's say there's a point here, right? This is our support vector. Xi, and we just basically want to find this quantity here, this length, gamma, right? Because that gives us the width of the margin. Okay, so just note that the value of gamma doesn't actually depend on the threshold, right? This value of T, it basically just shifts up and down the model. So I could consider the same model shifted downwards, right? So parallel, this would be W transpose X equals to 0. So just imagine that I'm drawing it parallel, even though it's a very poor drawing. W transpose X equals to M, right? And W transpose X equals to minus M. The point I'm trying to make is that the W vector, and if X is just shifted down here, this value of gamma doesn't change, right? Doesn't depend on T. So I'm going to do the analysis to find gamma based on having a threshold of 0, just to make life easier. Okay, so we can, basically what we have is W, we have X on this hyperplane here. Okay, so this is X, say I, and we want to find this gamma. So I did this last week, okay, but I'll do it again just to refresh. Okay, remember we said that this angle here is called theta, and we know that the dot product of W and X is the length of W, length of Xi times the cosine of the angle theta between them. Okay, and again, let me just specify that this is W transpose X equals 0, this is W transpose X equals to M. Okay, where M is the margin, or sorry, the kind of the distance. It's the shift between the hyperplanes. And if we rearrange this, we can write theta is equal to arc cosine W dot Xi over the length of W, length of Xi. Okay, which is what we did in the previous tutorial. Okay, again in the previous tutorial I defined this quantity phi, and we noted that theta plus phi has to be 90 degrees because W is perpendicular, so this angle, the total angle is 90 degrees. So phi must be equal to pi over 2 minus theta. Okay, and then the idea was to use the sine rule to try to compute this gamma. The rule is the sine of the angle is equal to the opposite over the hypotenuse. The opposite is this is gamma, and the hypotenuse is the length of this vector, which is just Xi. Okay, and gamma is equal to length of Xi, sine of phi. And we talked about this last week as well. Sine of phi is sine of pi over 2 minus theta. And we can just shift the sign to be the cosine of theta, right? Because pi over 2 minus theta is like cosine of theta. So gamma is equal to cosine theta. So if you're confused by this step, just go back to the previous tutorial and have a quick review. And then I can just basically plug in the value of theta. So cosine and arc cosine cancel out. The xi's cancel out, and we're left with w dot xi w. Okay, so this is the value of the margin, or the length of the margin. But note that we can simplify even more, because w dot xi, well, xi is on this hyperplane up here, right? And we know that w transpose x is equal to m for any point on this hyperplane. So this is just equal to m. Okay, so the margin is m over w. Now, what's common is to note that it doesn't actually matter what the value of m is, because we're able to rescale w and t to any value we want. Okay, so we can actually fix m equals to 1. So you'll always see basically this as t plus 1, t minus 1, and that gives us a margin of just 1 over w. Okay, so let me summarize what we know about SVM. Okay, so we want to classify everything correctly, and we want the fattest margin possible. Okay, and now we have the picture in mind where we actually have these two vectors, or hyperplanes, sorry, w transpose x equals to t plus 1, w transpose x equals to t minus 1, and our middle hyperplane here. Okay, so what I want to do is try to translate these objectives into some mathematical quantity. So how do you classify everything correctly? Well, we need that everything to the right side of this hyperplane is positive, right? And well, sorry, is part of the positive class, and we need everything to this side of this hyperplane to be negative. In other words, we want w transpose x minus t, okay, to be greater than or equal to 1. Okay, so let me just explain what's going on here. Remember, in the perceptron, okay, what did we want? We wanted yi w dot xi greater than 0, right? Because this means that, you know, the point is being classified correctly. Otherwise, we're making a mistake. This is exactly the same thing, except that I'm rewriting the w in terms of, I'm rewriting the dot product here, wxi, using the threshold parameter. Okay, and now I don't just want it to be greater than 0. I actually want it to be, so greater than 0 would mean that it's on this side of this middle line, but I actually want it to be on this side of this hyperplane. Okay, so we need it actually to be greater than or equal to 1. And the second condition, the fattest margin possible, well, we know the margin is gamma equals to 1 over the norm of w. Okay, so we want to basically find the largest gamma possible. Okay, and we can basically, to find the largest gamma possible, what we want to do is maximize gamma, which is equal to minimizing W, right, the norm of W, because if I want to make gamma bigger, that's equivalent to making W smaller. Okay, and this is equivalent to minimizing the half of W squared. The idea is that, if we want to minimize something, we're going to take derivatives. It's easier to take derivatives of the norm squared than it is of the norm, and because the squaring is monotonic, we'll actually get the same result. Okay, so for the argument, I should say, the W that achieves this will achieve this, and we put the half just for convenience, because if we're squaring, this is going to come down in the derivative, and we want things to cancel out. Okay, so those are basically the two objectives: make the margin as large as possible, classify everything correctly. Okay, and this kind of takes us to the definition of SVM, which is to find the weight vector and the threshold WT that minimizes this quantity. Okay, but we need to have a constraint, and usually you'll see this written as subject to yi W transpose xi minus t greater than 1 for all the data points. Okay, for 1 to n. Okay, so this is basically the idea behind SVM. This is the objective function. Now we've seen this before. Okay, this is easy to minimize or maximize or whatever, because we just take derivatives and we make it equal to 0. This part, the constraint, makes it a little bit different. Okay, so before we answer this question, let's look at this concept of constrained optimization. Okay, because what we did before, right? If I look at this function, for example, just the easiest example, and I ask you what is the argmin of x squared, well, you'll say f of x is equal to x squared, f prime of x is equal to 2x, make it equal to 0, and solve, we'll get x equals to 0, right? Okay, so you know the minimum is there. This is a little bit different, because we're saying, how do you minimize x squared such that, let's say, for example, you have a constraint that the absolute value of x has to be greater than or equal to 1. Okay, the reason this is different is because x equals 0 is no longer a solution, because it doesn't satisfy this constraint. So we need to figure out a way of computing solutions to these kinds of problems. We can look at this graphically, right? Where is this is 1, this is -1. So any point on the red actually is a solution to this, is a feasible point, or is a point that satisfies this condition, and the value that achieves the minimum is either exactly -1 or exactly 1. Okay, so this is called a constrained optimization problem. The constrained part is the fact that we have this extra requirement. Okay, and that's basically what this problem is. We have a thing we want to minimize, but we have a constraint that also has to be satisfied in the final solution. Okay. All right, so let's look at an example of constrained optimization and how you'd actually solve this thing. Okay, so before I explain or derive the SVM, I just want to go through an example how to solve constraint optimizations for a different problem. And the approach is called the method of Lagrange multipliers. Okay, so you probably would have heard of this if you've done any kind of optimization courses, but if not, I'll try to introduce it here, and this is kind of the approach I'll be using to derive the SVM. So let's just consider an example where we have some function xy, and we want to say maximize. So we want to choose x and y to maximize xy, but we have a constraint. Say the constraint is that 4x plus 4y is equal to say 10. Okay, so this is just some random constraint, but the solution that we end up getting has to satisfy this constraint. Okay, so to solve something like this, we set up something called the Lagrangian, which is a function of x, y. Okay, so the function of the original variables that we're trying to maximize with respect to, but also it considers the number of constraints that we have. So here we have one constraint, so we introduce an extra variable, I'll call it lambda, okay? And this lambda represents the one constraint. So if we had another constraint, say we had 2x plus, I don't know, 10y equals to 30, you know, maybe this doesn't make sense in this case, but we'd have lambda 1, lambda 2. Okay, so the number of constraints gives me the number of these extra variables. These are called Lagrange variables. Okay, so let's just go back to the original problem. What is the Lagrangian? The Lagrangian is the original function, so just x, y. Okay, minus lambda times the original, the constraint. Okay, the constraint, by the way, I should mention, needs to be 4x plus 4y minus 10 equals 0. So you need to have a 0 on the right-hand side. So you can just shift everything to one side to get this. And so we plug in the constraint as this. Okay, this is called our Lagrangian. And then the nice thing about the Lagrangian is you try to optimize it or maximize it just in the usual way that you would do a standard optimization problem. That means that we would take the partial derivative with respect to x, the partial derivative with respect to y, the partial derivative with respect to lambda, and we would just make them equal to 0 and try to solve. Okay, so let's differentiate with respect to x. We get y minus 4 lambda equals to 0. Here we get x minus 4 lambda equals to 0. And then finally, differentiating with respect to lambda, we'll get 4x plus 4y minus 10 equals to 0. Okay, now we can rearrange and try to figure out the value of lambda. Okay, so let me rearrange this one. This one gives us y equals 4 lambda. This one gives us x equals to 4 lambda. And if I plug in y and x values into this equation, I get 4 times x, which is 4 lambda, plus 4 times y, which is 4 lambda, should be equal to 10, which is the same as saying 16 lambda plus 16 lambda is equal to 10. So lambda is equal to 10 over 32. Okay, and then we plug this back in into our x and y. So 4 times 10 over 32 is equal to 40 over 32, which is equal to 5 over 4. And similarly, this is going to be 5 over 4. So x and y are going to be equal in this particular case. Let's just check the condition holds. 4x plus 4y equals 10. Okay, well, 4 times 5 over 4 is just 5. Plus 4 times 5 over 4 is 5. 5 plus 5 is equal to 10. So the constraint is met, and this value here, xy, is maximized. Okay, so this Lagrangian is basically what we're going to need to set up for the SVM case. In the SVM case, we have a slightly different optimization problem, because, so let's look at the SVM case. We want to minimize with respect to W and T half of the norm squared, subject to yi W transpose xi minus T is going to be greater than or equal to 1. Okay, that's what we wrote down here. Okay, this is different in a couple of ways, or well, in one way really. In the previous problem, we had a constraint that was 4x plus 4y equals to 10. Here we have an equality constraint. Here we have an inequality constraint. Okay, so we just move everything to the one side, so we can rewrite this as dub xi minus t minus 1 greater than or equal to 0. Okay, and then we can actually just set up our Lagrangian. Just note here we have how many constraints. We have a constraint for every observation, so we're actually going to have n constraints. Okay, so we're going to have n Lagrangian variables. Okay, so the Lagrangian in this case is going to be, so let me write L, W, T, and we're also going to have, well, let me call them alpha 1 to alpha n, and that's going to be the original function, okay, minus the constraints. So the constraints are going to be basically all these additional blocks, right? So alpha 1, y1, wx1 minus t minus 1 minus alpha 2, blah, blah. So all of these, so I can just rewrite them as the sum from 1 to n, alpha I, yi, wxi minus t. Okay, so this alpha I should be multiplied by the entire constraint, like this. Okay, now let's just expand this out a little bit. So first things first, this is going to be half W transpose, well, W dot W minus, if we expand this sum out, we'll get alpha I, yi, wxi plus sum from 1 to n, alpha I, yi, t, and then plus the sum of the alpha I from 1 to n. So I'm just expanding out these brackets carefully. Now we can rewrite this as, so note that this W doesn't have an index I, so we can actually take it outside. Okay. And similarly, the T here doesn't have index, so we can take it outside. And we finish it off with this sum. Okay, so that's our Lagrangian. Now the idea is basically we don't want to work with the, so this is this is the primal problem. Okay, so we're going back to that primal dual concept that we talked about at the start. So because this is a function of W, right? And we want to talk about it. We want to talk about the dual problem, which is getting rid of W. Okay, so one way to get rid of W is to consider. So what is the next step in the Lagrangian? It's to take the partial derivatives. So if we take the partial derivative with respect to W and respect to T, what do we get? Well, with respect to W, this term here becomes just W, right? This is like half W squared. And this term here, well, we just get rid of the W to get this. Okay, so this constraint is telling me that the optimal solution has to satisfy W equals to this guy. Okay, and you should hopefully recall that this is exactly the same expression for the dual perceptron. The alpha I here is different. It's not counting the number of mistakes, but the form generally is the same. And by the way, I forgot to say one thing. These alphas have to be positive. Okay, it doesn't make sense for these constraints to be negative. So just keep that in mind. Lagrange variables are always positive. Okay, but they don't have to be integers. So remember, in the dual perceptron, we were counting the number of mistakes, so they have to be 1, 2, 3, 4. Here, they can just be positive values, so they can be fractions or whatever. The second constraint, or the second derivative with respect to t, well, t just appears here. It just gives us that this sum has to be equal to 0. Okay, so that gives us two constraints that have to be true at the optimal solution. So the trick is basically to rewrite the Lagrangian having these constraints. Because we want to get rid of w, we can write every w in terms of this guy here. Okay, so half w dot w, right, is just equal to and let me just write alpha j, yj, okay. So that's this first term. The second term is minus w times this sum. Okay, and w is multiplied by the sum, so this is w times the sum. Okay, plus t times this guy. Well, if we take the second constraint, this guy is just 0, so we can just ignore it. Plus I equals 1 to n of alpha I. Okay, so this is our Lagrangian, rewritten to basically remove all mention of w. Okay, so this is completely in terms of just alphas. Now I can simplify this if you note that the first term and the second term are actually the same. So half minus this, I'm just going to get minus half times the sum. Again, I'm going to open up the summation to get alpha I, alpha j, yi, yj, xi dot xj. I'm running out of space here, but I just want to keep it all on the same page. I equals 1 to n. Okay, and this is the Lagrangian in terms of just alpha, right? In terms of no w, no t, no mention of w or t. Okay, and this is actually called the dual Lagrangian. Okay, so let me dual Lagrangian. Okay, and the dual variables are the Lagrange variables, are those alphas. Okay, so this is minus half and we call this the Lagrangian of the dual variables alpha 1 to alpha n. Okay, so I won't go into too much detail here, but you can actually solve the original minimization problem, original SVM minimization problem, by maximizing the dual, by solving the dual maximization problem. Okay, and if you're interested in why that is, you need to look up the KKT conditions, which I'm not going to cover here, but just you can basically just trust me that it does work out. If you're interested in why, you can look this up. But what this is saying is that there is some result that tells us that we can actually go from minimizing with respect to W and T to maximizing this Lagrangian with respect to the alpha parameters. Okay, and note that this problem is to take the argmax alpha 1 to alpha n of this function Okay, but we can't ignore the constraints that we had before. The constraints are that the alpha i's are positive. So subject 2. And the other constraint that we had was that the alpha I times the data yi, or the classes, is going to be equal to 0. Okay, so this is called the dual problem, and this is basically the problem that we'll work with, with SVMs. And you should note that it's pretty similar to the dual perceptron. This kind of term here is actually very similar. And the other thing you should note is that the data only appears in the objective through this dot product, which means that everything we said earlier about features, about kernels, works for SVMs, right? So you can actually replace this with kxi xj or phi xi dot phi xj, okay, depending on what you're doing. Okay, and that's kind of the reason why we would want to go from the WT optimization scheme to the alpha I optimization scheme, because it allows us to take advantage of the kernel trick. And so that is basically the idea of going from primal to dual. Okay, so you want to get to the idea of these, or the ability to represent data in a much higher dimensional space without paying the price. All right, so you don't really need to know how to derive this thing, but you do need to know how to work with this quantity, or actually how to solve this problem for a given data set. So let's consider the following example. So we have our data matrix, and we have our class labels. Okay, and so just to clarify, this is the point x1, x2, x3. So this is just a matrix, kind of like the first row here is my first example. It has class 1. Second example has class 1, and third example has class -1. If you look at the objective of the SVM here, okay, we actually have this yi, yj, xi, xj. So we have yi, xi dot yj, xj. So it's common to actually introduce this x prime matrix, which is basically the rows of x multiplied by their class. Okay, so in this case, 1 and 3 times 1 is just 1, 3, 2, 1, and then the last one multiplied by its class is 0, -1. Okay, and then what we really need is we need all the dot products between yi xi and yj xj for all possible combinations. And you should kind of convince yourself that this is just x prime multiplied by x prime transpose. Okay, so this would be 1, 3, 2, 1, 0, negative 1. And the transpose would be 1, 3, 2, 1, 0, negative 1. And this is equal to, okay, so how do we do matrix multiplication? We multiply this row by this. So this would be 10, 5, negative 3. Okay. And this is not exactly the gram matrix because the gram matrix is just the dot product between the x's, and here we're looking at the dot product between the x times the y's. So I'll just call it G prime. Okay, so this is a kind of a gram prime matrix. So using this, let me write out the SVM or the dual optimization problem. So this is going to be arg max. We have 3 data points. We're going to have 3 Lagrange variables minus half. Okay, well, the first term is going to be 10 alpha 1 squared, right? Because let me just write out the term. So here we're going to have alpha I, alpha j, g prime ij, right? Because this is the yi xi times yj xj, plus the sum of the alpha i's. Okay, this is the objective, subject to alpha I being positive and alpha I yi being 0. Okay, so I want to rewrite this in terms of our problem. The first term is going to have I equals 1, j equals 1, so this is going to be alpha 1 squared, and the coefficient g prime 1, 1 in the gram matrix, or the g prime matrix, is 10. So this is 10 alpha 1 squared, plus, and, you know, I'll leave this for you to work out, but basically you get 10 alpha 1 alpha 2, minus 6 alpha 1 alpha 3, plus 5 alpha 2 squared, minus 2 alpha 2 alpha 3, plus alpha squared 3, plus alpha 1 plus alpha 2 plus alpha 3, subject to alpha 1 greater than or equal to 0, alpha 2 greater than or equal to 0, alpha 3 greater than or equal to 0, and the loss condition being alpha 1 y1, which is just 1, plus alpha 2 y2, which is just 1, minus alpha 3 equals to 0. So this is the alpha I yi equals 0 condition here. Okay, so from this condition we can actually simplify alpha 1 plus alpha 2 is equal to alpha 3. So we can replace alpha 3, we can kind of make life a bit easier and just focus on 2 variables instead of 3 by rewriting alpha 3 in terms of alpha 1 and alpha 2. And this kind of simplifies things for us. And so if you do that, you'll get this problem. So after some simplification, which is pretty straightforward, you'll get 5 alpha 1 squared plus 4 alpha 1 alpha 2 plus 4 alpha 2 squared plus 2 alpha 1 plus 2 alpha 2. Okay, so this is our, you know, our Lagrangian, and we can basically take derivatives. So let me call this L alpha 1 alpha 2. We can take derivatives with respect to alpha 1. We get minus 5 alpha 1 minus 2 alpha 2 plus 2 equals to 0. The derivative with respect to alpha 2 is going to be minus 2 alpha 1 minus 4 alpha 2 plus 2 equals to 0. And then Doing some simple algebra and solving gives us the solutions, which I'll write here. Alpha 1 equals to 1 over 4. Alpha 2 equals to 3 over 8. And alpha 3, well, if we have alpha 1 and alpha 2, we know that alpha 3 is equal to alpha 1 plus alpha 2. So that's equal to 5 over 8. Okay, so what this tells us is that none of these alphas are 0, which means that they're all the xi's are support vectors. Okay, so to see that, let's actually go one step further and compute w. Right? How do we compute w? Well, if we go back a few steps, we know that w is equal to alpha I yi xi, right? The sum of the alpha I yi xi. So let's actually compute the value of w. So w is equal to the sum of the alpha I y xi, and this is going to be 1 over 4 x1 plus 3 over 8 x2 minus 5 over 8 x3. Okay, so this is actually just going to be 1 over 2. Okay, then to compute t, so how do we compute t? Okay, well, we know that we can actually compute t from any support vector because yi w xi minus t is equal to 1, right? These are all support vectors. So let me just draw the picture again. So in general, only the points on these lines, on these hyperplanes, are going to have alpha I not equal to 0. Everything else will have alpha I equals to 0. Okay, so in other words, W transpose xi for any of these points on the margin will be exactly equal to 1, right? We'll achieve exactly the point here. So we can actually retrieve t by just solving this equation. So let's take the third one. Okay, the third point has y3 equals to -1, wx3 is 1/2 times x3, which is 0, 1, minus t equals to 1. So this tells us that -1/2 minus t is equal to 1. So t is equal to 3 on 2. Okay, so that means that our weight vector, and so we have our model in terms of w and t, and actually let's actually just plot this out. Well, I generated a plot that's probably going to be much neater. So here, see these blue points, these correspond to x1 and x2. The red point corresponds to x3. Now, the orange line is w dot x equals to 3 over 2, the threshold that we computed. And the green lines are the +1, -1 surfaces, hyperplanes. And so hopefully you can see that these are definitely support vectors because they're actually on the line, right? And if we take any point inside here or inside here, the alpha given to it should actually be 0. Okay, so that's the kind of the visualization of the support vector machine that was learned. Okay, and the final step is to compute the margin. Okay, so if we want to compute the margin, Well, the margin is just going to be 1 over the norm of W, right? We computed that earlier. So this is going to be 1 over the square root of 1 squared plus 1 over 2 squared, which is 1 over the square root of 1 plus 1 over 4, which is just, after some simplification, 2 over square root of 5. Okay, and that's kind of basically it for the SVM. So make sure, even if you're not that interested in kind of understanding why we get this KKT condition, that you're comfortable with solving SVM problems, for simple data sets at least.